For the past 15 years, physicists have been quietly panicking over a tiny discrepancy that threatened to break our entire understanding of the universe. We are talking about the proton radius puzzle, an intense debate over the exact size of a hydrogen atom's proton. Different measurements were giving conflicting answers, and this was a huge deal because it hinted that we might need entirely new physics to explain it. But today, it looks like the debate is finally winding down and the standard model of physics is safe. The latest experimental measurements published in major journals have basically put the final nail in the coffin of this puzzle. To understand why this was such a big deal, we have to look at how atoms actually work. Most of us learned the classic model in school where electrons orbit the nucleus in neat little circles, like planets around the sun. But quantum mechanics tells us the reality is much weirder. Electrons are not really orbiting. They are essentially waves that only take on particle-like properties when we try to measure them. They exist in a fuzzy, cloud-like state, encompassing all probabilities of their position at once. The proton itself is also fuzzy, made of 3 quarks bound by the strong nuclear force. So how do you measure the radius of a cloud? Physicists look at the charge density. The radius is basically the distance at which that density drops below a certain threshold. For a long time, the accepted radius of a proton was 0.876 femtometers. But then, back in 2010, a team of scientists decided to replace the electron in a hydrogen atom with a muon. A muon is basically a heavier cousin of the electron. Because it is nearly 200 times heavier, it orbits much closer to the proton, making it 10 million times more sensitive for measurements. They fully expected to get the standard 0.876 measurement, just with better precision. Instead, they got 0.841 femtometers. That is 0.0000000000003 millimeters smaller. It sounds insignificant to you and me, but in physics, that is a massive 5 standard deviations away from the accepted value. This discrepancy launched a decade and a half of frantic experiments. Was our theory of quantum electrodynamics flawed? Was there a mysterious new particle we had not discovered yet? Subsequent tests gave completely mixed results. Some confirmed the smaller size, while others supported the larger old measurement. Finally, 2 recent breakthrough experiments using regular hydrogen in vacuum chambers controlled by highly precise lasers settled the score. Both concluded that the proton indeed has a radius of about 0.84 femtometers. The 2010 measurement was right all along. While it is incredibly impressive that we can measure something down to parts per trillion, a lot of physicists are actually a little disappointed. They were really hoping this discrepancy would lead to the discovery of an entirely new physical force. Instead, it's just a massive confirmation that our current standard model is incredibly accurate.